pertemuan ke-7 sebelum UTS, pengantar rekayasa dan desain. Ya, topik ke-7 kita ini Mechanical Engineering. Capaian pembelajaran kita di akhir program studi, mahasiswa diharapkan mempunyai kemampuan merancang dan melaksanakan eksperimen, termasuk menganalisis dan menginterpretasikan data secara ilmiah menggunakan metode ilmiah. Ini terkait dengan program Learning Objective 8, PLO 8. Di akhir semester, mahasiswa diharapkan mampu memahami beberapa disiplin rekayasa. Ini terkait dengan course Learning Objective 3, CLO 3. Di akhir minggu, mahasiswa mampu menganalisa perkembangan teknologi teknik mesin yang terkait dengan kemajuan ilmu pengetahuan. Ya, inilah terkait dengan topik kita dalam minggu ini. Pokok bahasan kita konsep Mechanical Engineering, why, what, how. Ya, metodologinya flip classroom. Studi kasus kita, ya memang belum sampai ke sana. Tadinya mau mobil listrik. Referensi kita dari Philip Kosti, Exploring Engineering and Introduction to Engineering and Design. Ya, lecture note-nya ada di sana. Di akhir kuliah kita, nanti jam 9, tadi saya mau coba upload problem kota, ini essay yang dikumpul nanti di akhir kuliah, jam 11.30, ya, 11.30, atasnya essay, karena ini terkait nanti kita latihan, terkait dengan model UTS-nya ada 25 multiple choice dan 1 essay. Jadi ini saya coba bikin soal essay, tapi ya bukan ini soalnya. Ini hanya sebagai contoh saja, kurang lebih mungkin gambarannya seperti ini. Di problemnya problem kota, tapi filenya kayaknya belum terkirim. Ya, nanti di akhir kuliah. Nah, kita masuk dulu lecture note-nya. Ya, sudah di LMS, bisa dibuka. Di LMS bahannya mudah-mudahan ini Mechanical Engineering, ya. Mechanical Engineering. Topik bahasan kita, ya. Introduction, ada 2 pokok bahasan utamanya, thermal design, ya. Ruang lingkupnya heat transfer, fluid mekanik, termodinamik, dan mechanical design, ya. Mechanical behavior, machine element, dan manufacturing proses. Ya. Ada beberapa nanti video yang nggak mungkin kita bisa putar di sini, jaringannya nggak kuat, tapi saya sudah masukkan di dalam modul ini, ya bisa nanti secara offline dilihat, dan nanti setelah akhir kuliah mudah-mudahan rekamannya bagus, tidak ada masalah, nanti saya akan upload bersama dengan video pendampingnya. Ya. Introduction, ya, terkait dengan ruang lingkup dari Mechanical Engineering. Ya. Ruang lingkup Mechanical Engineering ada 2 bagian besar, yaitu thermal design dan mechanical design. Ya. Mechanical design dan thermal design. Bagaimana kita merancang, ya, heat transfer, perpindahan panas, ya, mekanika fluida, ya, bagaimana termodinamika, ya itulah terkait dengan thermal design, mechanical design, bagaimana perilaku mekanik, ya, bagaimana elemen-elemen mesin dirancang, bagaimana proses manufacturing dilakukan, ya. Nah, kita beruntung di era ini, ya, kita banyak bahan, ya, yang sudah bagus, saya katakan sudah bagus, dan sudah terrecord, sudah terpublis secara sosial, secara YouTube, ya kita bisa lihat seperti Mechanical Engineering dalam video ini nanti, ya, coba dilihat bagaimana dia menggambarkan, ya, dunia teknik mesin, ya, nanti silakan dilihat atau lihat videonya setelah kuliah ini, nanti saya akan masukkan, ya. Jadi kita nggak bisa putar ini, ya, tapi bisa nanti diputar secara offline.
Mechanical engineers have changed the world, you could even say the course of history. Not just once, but countless times. Because they've identified problems that were holding humanity back, and they solved them. Things were too big and heavy to move. Travel was too difficult, distances too far, our bodies were too weak. If you can think of an invention that revolutionised the way people live, odds are it was created by mechanical engineers. And I don't think I'm being biased. Theirs is the field of engineering that focuses on the design, construction, operation and maintenance of machines and mechanical systems. Pretty much anything that moves. And since the beginning, mechanical engineering has faced a great many challenges and solved a lot of problems. The examples are too many to count, but consider things like the steam engine, airplanes, robots, and biomechanical suits. The engineers behind all of these devices were able to find solutions to big problems. And of course, they faced difficulties along the way, but great efforts almost always do. Back in the day, if you wanted to get somewhere, you would have had two options, your own 2 feet or a horse. And if you wanted to take a heavy load with you, you needed a carriage, wheels. The invention of the wheel is one of the oldest roots of mechanical engineering, along with all of the simple tools that went into building the carriage itself. If we include the simple levers that were used to open gates and bring down bridges, we'd have a great but primitive base of early mechanical engineering. But horse-drawn carriages aren't very fast. A horse needs rest and food, so it would be generous to say you could cover 80 kilometres a day. This gave the engineers of the past a problem. As the world opened up, it became more important to cover distances in less time, and horses just weren't cutting it. They needed something faster. They needed an engine. Making its first appearance in the early 18th century, the steam engine marked a major turning point in the development of modern mechanical engineering. It was proposed that a steam engine could do the work of 10, 15 or even 20 horses, and you wouldn't even need to bother with any hay or manure. This brings us to Thomas Newcomen, a British inventor who developed the first successful steam engine with a piston in 1712. In his design, atmospheric pressure pushed the piston down after the condensation of steam had created a vacuum in the cylinder. Its original use was to draw water out of the Cornish tin mines after Newcomen found how expensive it was to use horses to pump the water. Then along came the Scottish inventor James Watt. In 1763, while repairing one of Newcomen's engines, Watt realised that about 3/4 of the energy from the steam was going to waste, used only to heat the chamber of the engine. His solution was to have a separate condenser. The steam would then be condensed in a chamber separate from the piston chamber, so that the condensed steam didn't go to waste. Keeping the two processes separate allowed for continued rotary motion, which was really important because it allowed for a more consistent source of power. Watt's invention came to be widely used to run machines in the factories that drove the Industrial Revolution. Watt went on to be the first engineer to be commemorated in Westminster Abbey with a large white marble statue erected in his memory. He also had his last name recognised as a unit of power, which is perhaps one of the highest honours that an engineer can get. But steam engines really came into their own, especially in the realm of transportation, in the locomotives of the 19th century. George and Robert Stephenson, an English father-son duo, are famous for their early steam locomotive, which they called, aptly enough, locomotion. In 1825, it became the first public passenger train carrying 450 people at 24 kilometres an hour. Quite a bit faster than a horse. But while wheeled vehicles allowed people to travel more quickly on land, transportation was still limited by bodies of water and rough mountainous terrain. If engineers could figure out a way to get people to fly, all of that could be avoided. This problem-solving led to the invention of aircraft. The first powered aircraft to take flight was the Wright Flyer in 1903, which was designed by Wilbur and Orville Wright and used a 12-horsepower gas engine. Orville flew the Wright Flyer on its maiden voyage, travelling 36 metres in 12 seconds. But the best flight of the day belonged to Wilbur, who travelled over 255 metres in 59 seconds, or a speed of about 15 kilometres an hour, earning him some serious bragging rights. Soon after the Wright brothers' accomplishment, World War I sparked a burst of aircraft innovation. Engineers began using metal in structures of airplanes and better engines, allowing them to reach higher speeds and altitudes. Then in 1930, Sir Frank Whittle obtained his first patent for a turbojet engine. But it wasn't until the outbreak of World War II that the British government had a compelling reason to support his work. By 1941, Whittle's engine featured a multi-stage compressor, a combustion chamber, a single turbine and a nozzle, which was a big improvement since previous engine designs only had an internal combustion engine and a propeller. Jet engines outperformed the older designs, flying farther, faster and cheaper too. These advances ultimately made commercial air travel possible, and soon people were travelling where once only the birds had ruled. But mechanical engineering doesn't stop in the air. Beyond planes, we've sent satellites into orbit, astronauts to the moon, and spacecraft carrying rovers all the way to Mars. The aerospace side of engineering actually arose from the mechanical field. And much of what has allowed us to build these machines that move us is another big part of the mechanical engineering field, robotics. For most of industrial history, humans have been at the centre of our workforce. But humans have their limits. Some things are too big and too awkward to move, while other processes need finer precision than the human hand allows. Industrial environments are also often uncomfortable and sometimes even dangerous. And that's where robots and automation come in. The first industrial robot, called Unimate, appeared around 1960. It was designed by American inventor George Devol Jr., who worked with engineer and entrepreneur Joseph Engelberger to get it into factories. Unimate robots had up to 6 fully programmable axes of motion and could handle parts weighing up to around 225 kilograms at high speeds. They soon joined the assembly line at a General Motors plant, where they took die castings from machines and welded them onto auto bodies. Since then, robots have gone beyond manufacturing, showing up in our homes to clean the floors and even hospitals to perform surgeries. But as their applications get more advanced, engineers have more and more factors to consider. They need to worry about how well robots sense their surroundings, how they move and manipulate their environments, and much more. It's possible one day that you'll have robots in many of the places you could imagine a human working. I mean, we're seeing that now. And speaking of humans, you can think of the human body as just a super complex mechanical system of its own, made up of links and connecting joints, and this is where biomechanics comes in. Engineers need to take into account the stress, load, and impact that our bodies can withstand, and apply it to machines that are modelled on us. Advanced biomechanics is one of the newest divisions of mechanical engineering. From it, we're already seeing the beginnings of exoskeleton suits, limbs that move like their biological counterparts, and other robotic implants. One of the more impressive projects is the Berkeley Lower Extremity Exoskeleton. Funded by the Defense Advanced Research Project Agency in 2000, this device is designed to provide mechanical support to allow nearly anyone to carry larger, heavier loads than they could ever lift on their own. The ability to carry heavy loads is often a problem for soldiers and disaster relief workers, so finding a solution to this is pretty important. But the problems are many. For one thing, power sources for exosuits are often too heavy or cumbersome, but the Bleaks, as it's called, overcomes this by using a small hybrid power source that delivers hydraulic power for the suit's locomotion and electrical power for its computer. The first prototype was recently introduced, consisting of 2 powered anthropomorphic legs, a power unit, and a backpack-like frame. Using the frame, a person can carry a heavy load, but only have it feel like a few pounds. In similar fashion, Berkeley is also behind the Austin project, which aims to develop exoskeleton systems for people with mobility disorders. So it's almost as if we've gone full circle, from the inventors who developed the first steam engine to replace the horse, to the biomechanical engineers who are using robotics to simulate the most basic means of transportation: walking. Those are some of the very big problems that mechanical engineers have managed to solve. And when it comes to the problems that we still face today, from driving in traffic to getting food and water to remote areas, you can bet that mechanical engineers will be there to tackle them. So today we learned all about many different areas of mechanical engineering, beginning with the steam engine. We then moved on to aircraft and the work behind them, and we finished by going into the more modern areas of robotics and biomechanics. In the next episode, we'll explore electrical engineering, its history, and the work that electrical engineers do. Thanks for watching, and I'll see you then. Crash Course Engineering is produced in association with PBS Digital Studios. You can head over to their channel to check out a playlist of their latest amazing shows, like PBS Spacetime, Above the Noise, and Physics Girl. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.
Jadi dia menjelaskan thermal design di sana, yaitu heat transfer, perpindahan panas. Yaitu perpindahan panas memiliki aplikasi dalam desain pertukaran panas pendinginan mesin, ya, AC, dan pendinginan elektronik, dan banyak sekali konsep-konsep perpindahan panas dari dingin ke panas, panas ke dingin untuk pengkondisian mesin, pengkondisian udara, ya. Bagaimana aplikasi dari perpindahan panas ini, heat transfer ini banyak di sekitar kita, di sekitar kehidupan kita. Ya. Topik keduanya mekanika fluida. Mekanika fluida mencakup bagaimana perilaku fluida di area terapan seperti jaringan perpipaan, sistem hidrolik, bearing, mesin turbo, dan airfoil, ya. Seperti di pengeboran minyak, ya, baik itu yang lepas pantai, bagaimana mekanika fluidanya sangat berperan di sana, ya. Jadi kalau kerja di bagian perminyakan, ya mekanika fluida ini sangat berperan, ya, di sana. Termodinamika adalah studi tentang kekekalan energi di bidang terapan, seperti siklus mesin dan pendinginan, pembangkit listrik, dan pembakaran. Bagaimana termodinamika, ya, itu terkait dengan kekekalan energi, perpindahan satu energi ke bentuk energi lain dalam suatu siklus, ya. Kekekalan energi pada dasarnya energi ya hanya bisa berubah bentuk, ya, tidak ada yang hilang tapi berubah bentuk, berubah fungsi. Ya. Kesetimbangan termal. Panas sebenarnya hanyalah bentuk energi lain yang disebut energi panas. Ya. Ketika dua benda pada suhu yang berbeda bersentuhan dengan panas, mereka bertukar energi. Ya, dalam hal ini energi panas. Benda yang lebih panas memberikan energi termal ke benda yang lebih dingin sampai terjadi suhunya sama atau keseimbangan, kesetimbangan, di mana titik tersebut dikatakan berada dalam keadaan kesetimbangan termal. Ya. Jadi terjadi pertukaran panas sampai mendapatkan suatu titik keseimbangan disebut kesetimbangan termal. Perpindahan panas, ya. Kita lihat pada gambar bagaimana terjadinya perpindahan panas, apa yang disebut dengan radiasi, konveksi, dan konduksi. Ya. Ada tiga parameter yang penting di sana, apa yang disebut dengan konduksi, ya, kemudian apa yang disebut dengan konveksi, dan apa yang disebut dengan radiasi. Ya, dalam teknik perpindahan panas mengacu pada energi panas yang lewat antara benda, baik dengan konduksi, ada konduktornya, ada benda padatnya di sana, ya. Konveksi termal, ya, dalam cairan, kita lihat di sini bagaimana dia berpindah, dan radiasi, ya, ke udara. Konduksi termal, ya, ada persamaan dasar untuk laju perpindahan panas konduksi stabil disebut dengan hukum konduksi Fourier. Ya, ada hukum konduksi, yaitu suhu panas, ya, delta lah, suhu dingin terhadap ketebalan dari suatu dinding atau plak, ya, di mana terjadi perpindahan panas itu. Ya, ada suatu konstanta yang disebut konduktivitas termal material, ya. Jadi ada material memang dia mengantar panas, tentu faktor konduktivitasnya, ya, di luas permukaannya akan tinggi. Ada memang dia bukan pengantar panas, ya. Jadi laju perpindahan itu adalah satuannya adalah watt. Ada permukaan panas ditentukan oleh permukaan dari plat, ya. Ada selisih panas, ya, yang panas terhadap yang dingin, terjadi perpindahan panas di permukaan suatu benda. Ya. Konveksi. Persamaan dasar untuk laju perpindahan panas konveksi dikenal sebagai hukum pendinginan Newton. Ya. hukum pendinginan Newton. Satu lagi konveksi termal, ya. Ada dua jenis konveksi alami dihasilkan oleh perbedaan kepadatan dalam fluida yang dihasilkan oleh perbedaan suhu dalam fluida, misalnya seperti dalam kenaikan udara panas. Ya. Konveksi paksa fluida bergerak yang dihasilkan oleh pompa atau kipas ini digunakan dalam sistem pemanas dan pendingin udara, ya, pendingin elektronik, dan dalam beberapa teknologi lainnya. Ada konveksi alami, secara alami dia melakukan perpindahan, ya, dan ada yang paksa. Radiasi termal. Laju radiasi termal dinyatakan oleh hukum radiasi Stefan Boltzmann. Ya. Ada yang disebut laju perpindahan panas atau radiasi dalam watt, itu ditentukan oleh laju perpindahan panas radiasi. Ya. Benda hitam didefinisikan sebagai benda apapun yang emisitasnya, ya, satu sempurna, dan benda yang memantulkan sempurna memiliki emisitas 0, ya, emisitasnya 1 menyerap, dan yang memantulkan sempurna memiliki emisivitas 0, ya, memiliki emisivitas 0, ya. Dan ditentukan oleh konstanta Stefan Boltzmann, ya, dia menemukan konstanta Stefan Boltzmann dalam satuan watt per meter kuadrat, ya, derajat Kelvin pangkat 4. Dikali suatu perbedaan suhu, ya, suhu pada lingkungan terhadap suhu permukaan, ya. Jadi suhu lingkungan di sekitarnya dan permukaan, ya, kita dapat menentukan apa yang disebut dengan laju perpindahan panas radiasi atau W. Itulah konsep dari radiasi termal yang ditemukan oleh Stefan Boltzmann, ya. Berdua mereka menemukan formula itu, ya. Konsep radiasi termal bisa kita lihat dalam gambar berikut, ya. Ada sumber panas, boiler, ya. Bagaimana aliran, ya, aliran panas itu bergerak, ya, bergerak dan berfungsi, dan akhirnya memiliki suatu fungsi untuk memanaskan suatu air. Ya, ini aplikasi dari energi terbarukan fotovoltaik, ya. Jadi aplikasi dari fotovoltaik, bagaimana dia bisa digunakan, ya, digunakan untuk sumber air panas untuk mandi. Ya. Jadi dari energi matahari, bagaimana dia dipindahkan, dia menjadi dalam bentuk air panas. Jadi ada perpindahan di sana, ada konsep perpindahan panas, ya, dan konversi energi. Ya. Pompa untuk mengalirkan, ya, aliran panas. Ya, itu lebih lanjut, lebih detail, kita bisa lihat video transfer, ya, dari crash course engineering yang seri 14 ini, nanti bisa dilihat, ya, secara offline. Ya.
Whether you're heating up leftovers from last night or just trying to stay cool in the summer, Heat transfer is everywhere. In some ways, the world is literally built around it. Any well-engineered building is designed and made out of materials that help keep the inside of the building at a good temperature, even during bitter blizzards or horrendous heat waves. A furnace or AC will only get you so far. Without protecting against heat transfer, you might as well try to air condition your whole neighbourhood. A big part of engineering is using your knowledge of natural processes to keep them from interfering with whatever you're trying to do, or in some cases, taking advantage of those processes. So without a solid understanding of how and why heat moves the way it does, your designs won't be very successful, especially if you've just discovered a tropical island. So, this tropical island, it's small, totally deserted, and seems like the perfect place to build that vacation home you've always dreamed of. The tropical weather is really nice, but it's also hot. Very hot. So you'll probably want to design your house to keep the heat out and the cold in. In other words, you'll want to prevent as much heat transfer as possible. Even though heat isn't a fluid itself, heat transfers in a way that's kind of similar to the fluid movement we've talked about in past episodes. When fluids move, there's always a driving force behind them, specifically a difference in either pressure or velocity. With heat transfer, the driving force is a difference in temperature. In fact, if you don't have a temperature difference, you can't have heat transfer. Period. If you have two boxes right next to each other and they're both at the same temperature, then one of the boxes won't randomly start giving its heat energy away to the other one. But if you're watching this video on your laptop and it's, well, on top of your lap, then your legs might be warming up as the heat is transferred to them from your laptop. That's because right now your laptop is warmer than your skin. And when heat passively transfers, it always moves from a higher temperature to a lower one. You'd have to use the cycles and work energy we talked about before, basically an engine, to make it move in the opposite direction. And unless you have perfect insulation, which is practically impossible in most settings, then a temperature difference will cause heat transfer. So this house you're building is going to heat up from the warm tropical air no matter what. But there's a lot you can do to slow down the process. There are three main types of heat transfer to look out for: conduction, convection, and radiation. With conduction, heat energy is transferred by the collisions of molecules or other particles. When two things touch, the faster moving molecules of the warmer object crash into the slower moving molecules of the colder object, transferring energy that heats them up. In your house, that will cause heat transfer through the layers of the walls. As the outer layer warms up, conduction will transfer the heat through to the cooler inner layers. To slow this down, you'll want to build the walls out of a material with low thermal conductivity, something that doesn't transfer heat well. Copper, for example, has a high thermal conductivity, so if you made your walls out of it, you'd effectively be making a giant sauna, which doesn't sound like a great place to live. For one thing, it would probably be a burn hazard. Materials like brick and drywall, on the other hand, have lower thermal conductivities, so they'd be much better choices. Anything that sold as insulation also has a very low thermal conductivity, so you'll probably want some layers of that too. The thicker these layers, the more resistant the walls will be to heat transfer by conduction. Specifically, they'll have more of what's called thermal resistance, which is defined as the thickness of the layer of the material divided by the material's thermal conductivity and the area of the layer. All this means is that materials with a lower thermal conductivity have a higher thermal resistance, and that a thicker layer will also have a higher thermal resistance. But if there's more area for heat to be conducted through, that will lower the thermal resistance. Thermal resistance is also equal to the temperature difference divided by the heat transfer rate, which also makes sense. It means that for a given temperature difference, materials with a higher heat transfer rate will have a lower thermal resistance, and vice versa. You can use this equation to determine the level of thermal resistance you'll need if you want a low rate of heat transfer for the temperature difference you'd expect to have in the layers of your walls. And the resistance of the different layers adds up. So the total thermal resistance of the walls is equal to the resistance of each layer combined. It's like putting on layers of clothing on a cold day. The more layers you have, the lower your rate of heat loss will be, and the easier it is to stay warm. So for your house, if the drywall and brick don't have enough thermal resistance to keep the inside cool, you can add layers of insulation to up the resistance. That takes care of the heat transfer within the walls, but there's more going on outside of them, which brings us to the second method of heat transfer: convection. The transfer of energy by the physical movement of a fluid, which in engineering can be a liquid or a gas. As a fluid moves against or across a surface, it can add or take away heat. For example, as air heats up, its particles spread out, lowering its density. That warmer air rises, taking heat energy with it, and is replaced by cooler, denser air. That's called natural convection because variations in the temperature of the fluid create natural movement without any external forces. There's also forced convection, where something external like a fan or the wind moves the fluid. Heat transfer by convection actually involves some conduction, especially at first. When the warm outside air comes into contact with your house's walls, it creates the no-slip condition we've talked about before, where the layer touching the surface comes to a stop. Right on top of that, there's what's called a boundary layer, where the air is moving, but slowly. The lower velocity slows down the rate of heat transfer, creating a thermal boundary layer where there's more conduction between the particles and less convection. Beyond the boundary layer though, heat transfer mostly happens by convection, through the faster moving air. You can measure how much heat is being transferred by convection using what's known as the convective heat transfer coefficient, represented by the letter H. It's proportional to the thermal conductivity of the fluid over the thickness of the boundary layer, which just means that thinner fluids with higher thermal conductivity will transfer more heat. Makes sense. H also depends on how fast a fluid is moving. The less a gas moves around, the less heat is transferred through convection. That's why windows often have double panes. The air trapped between the layers of glass can't move very much, reducing the heat transfer. So double pane windows are probably a good idea for your house. There's not much else you can do to minimize the effects of convection, since you can't really control what the air does as it moves around outside. But you can reduce the effects of the last type of heat transfer, radiation. Radiation is the transfer of energy in the form of electromagnetic waves. And in this context, we're talking about any electromagnetic waves, not just the cancer-causing kind. You feel this radiation every time you walk outside and bask in the sun or warm up by a fire. Unlike conduction and convection, radiation can happen without any contact between the heat source and the object. That's why heat energy from the sun is able to reach the Earth. Reflective coatings can help reduce the heat transfer from radiation a little, since they absorb fewer electromagnetic waves. But when it comes to radiation, where your house is will be much more important than what it's made of. Since the sun will likely be the biggest radiative source, you'll want to build the house somewhere where it won't get too much direct sunlight. So there's a lot of factors to consider when you're trying to minimize heat transfer. But with a shady spot, walls with lots of thermal resistance, and some double-paned windows, you should have a pretty comfortable place to hang out on your tropical island. So today, we learned all about heat transfer and the different mechanisms behind it. We started with conduction and learned about the thermal conductivity of materials. Then we moved on to convection and boundary layers, learning that convection can be both forced and natural. Finally, we covered radiation and how it differs from the other two methods, in that it doesn't need an intervening medium to transfer heat energy. Next time, we'll talk about how we can use what we just learned about heat transfer and apply that to heat exchangers. Crash Course Engineering is produced in association with PBS Digital Studios. You can head over to their channel to check out a playlist of their amazing shows, like It's Okay to Be Smart, Above the Noise, and Global Weirding with Catherine Hayhoe. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.
Fluida, cairan atau gas, ya. Cairan itu bisa berupa cairan atau gas. Hitungannya fluida. Bagaimana mekanika fluida? Ya. Ya, menunjukkan dinamika. Ya, mekanika fluida ini menunjukkan dinamika. Dinamika benda bergerak di bawah gaya, mekanika. Ya. Dinamika dari suatu benda bergerak di bawah gaya. Jadi mekanika fluida itu berhubungan dengan statika fluida dan dinamika fluida. Ya. Fluida yang statis dan fluida yang dinamis. Ya. Cairan dicirikan dengan densitas, tekanan, dan viskositas. Apa itu densitas? Ya, densitas dari cairan didefinisikan sebagai massa persatuan volume. Ya. Tekanan dari suatu cairan didefinisikan sebagai gaya persatuan luas. Viskositas didefinisikan sebagai hambatan fluida untuk mengalir. Aliran fluida dapat berupa laminar atau turbulen. Laminar itu apa? Aliran yang terjadi pada kecepatan rendah ketika fluida mengalir dalam lapisan paralel yang meluncur melewati satu sama lain seperti kartu remi, ya, meluncur, ya, yang suka kartu remi itu tahulah seperti apa, dia pelan diambil, gitu. Turbulen ditandai dengan gerakan fluida yang turbulen, kacau, ya, turbulen, yang biasa naik pesawat ada turbulensi, ya, udara, perputaran udara yang bisa mengganggu kestabilan, ya, turbulen, kacau, ya, pergerakan, ya, apakah itu cairan, apakah gas yang tidak teratur, ya. Nah, tokoh yang mengembangkan mekanika fluida itu salah satunya adalah Reynolds, ya. Dia memberikan suatu Reynolds number, suatu definisi Reynolds number itu fungsi dari densitas, ya, dan viskositas fluida, ya, dan kecepatan fluida, sehingga dia bisa mendefinisikan berapa ya, faktor kecepatan fluida, ya, yang menentukan berapa Reynolds number-nya, ya, dalam suatu pipa yang berdiameter tertentu, berdiameter D. Nah, kemudian dimaknai apa makna number dari Reynolds ini dalam suatu aliran fluida, dalam suatu pipa. Jika dia lebih kecil dari 2000, angka 2000, maka fluida itu berjalan dengan lambat atau laminar. Kalau dia di atas, ya di sekitar, ya di atas 4000, maka dia termasuk dinamis, ya, bergerak secara dinamis. Kalau angka Reynolds number-nya di antara 2000 sampai 4000, maka dia transisi, ya, antara laminar dan turbulen. Jadi 4000 adalah dia sudah perpindahan fluidanya termasuk turbulen, ya, disebut dengan turbulen, ya. Laminar 2000, di antara 2000 4000 dia masuk kategori dari transisi. Untuk apa kita perlu menggunakan ini? Untuk bisa kita kontrol, ya, fluidanya bisa dikontrol. Statik fluida, yaitu fluida statis, ya. Untuk fluida tak termampatkan saat diam, jadi tidak termampatkan saat diam. Ada suatu persamaan statika fluida, ya, fungsi dari gravitasi, ya, dan ketinggian dari suatu fluida, sehingga kita bisa mendefinisikan suatu tekanan yang ada pada fluida itu fungsi dari gravitasi, ya. Fungsi dari gravitasi, ketinggian, dan suatu konstanta, ya. Kemudian fluida yang dinamai dengan dinamik fluida, fluida dinamis. Fluida ini dapat dimampatkan dalam gerakan stabil, dapat dimodelkan antara satu titik 1, titik 2 dalam aliran yang dikenal dalam persamaan Bernoulli, ya. Dinamika fluida, fluida yang dinamis itu persamaan Bernoulli akan memodelkan, ya, hubungan antara tekanan, kecepatan, gravitasi, dan ketinggian, ya. Bagaimana Bernoulli memberikan suatu persamaan yang menghubungkan antara tekanan, ya, ketinggian, kecepatan, dan gravitasi. Topik selanjutnya yang terkait dengan thermal yaitu termodinamika, ya. Termodinamika, dia mempelajari energi dan konversinya, ya, dari satu bentuk ke bentuk lain, ya. Ilmu termodinamika ini mempelajari konversi energi dari satu bentuk ke bentuk lain. Bisa kita lihat apakah dalam sistem yang terisolasi, ya, dalam arti baik massa maupun energi tidak dapat melintasi batas sistem, dia diisolasi, bagaimana perpindahan energi dari sistem yang terisolasi, apakah sistemnya itu tertutup, ya, dibatasi oleh ruang lingkup tertentu, massa tidak dapat melewati batas sistem, tetapi energi dapat, ya. Apakah di open system, ya, baik massa seperti gambar yang ketiga, baik massa maupun energi, ya, dapat melintasi batas sistem, ya. Jadi ada 3 model. Yang pertama, massa maupun energinya tidak bisa melintasi batas yang sudah diisolasi, sudah diberikan, ya. Ya tentu, ya banyak penggunaannya ini kan, ya. Banyak penggunaan, dia massa maupun energinya dia terisolasi. Nah, closed system itu namanya isolate system. Closed system, massanya tidak dapat melewati batas, tapi energinya dapat melewati, jadi panasnya bisa keluar, ya. Panas bisa keluar dari batas yang sudah diberikan. Ya, microwave yang isolate seperti microwave, ini seperti kompor, kita lihat, ya, massanya tidak dapat melewati batas, ya, dia tetap, kalau isinya air, tetap air di situ, ya, tapi panas, energi panasnya bisa keluar, ya, di sekitarnya akan terpengaruh, itu namanya closed system. Open system, ya, open system, massanya bisa keluar, ya, airnya tumpah, ya, air tumpah atau diisi air, dan energi dapat melintasi batas sistem. Jadi panasnya dalam massanya juga keluar, ya, dia mengalir, ya. Bagaimana dia mengalirkan air panas, misalnya dalam contoh open system ini, ya, akhirnya dia bercampur dengan air dingin menjadi sumber panas buat mandi. Ya, kira-kira kita bisa melihat bagaimana hukum termodinamika, ya, merumuskan bagaimana perpindahan panas, perpindah bentuk konversi energi dari satu bentuk ke bentuk lain, ya. Dia misalnya menghasilkan uap, ya. Yang ketiga ini menghasilkan uap. Uap air bisa menggerakkan turbin uap bisa menggerakkan generator menghasilkan energi listrik, ya. Energi listrik menggerakkan mesin, ya. Terjadi konversi energi, ya. Hukum-hukum yang mendasari itu adalah hukum termodinamika, ya. Maka dikenallah hukum pertama termodinamika yang menyatakan bahwa energi disimpan, artinya energi tidak dapat diciptakan atau dihancurkan. Tetapi energi dapat diubah dari satu bentuk energi, misalnya kimia, menjadi bentuk energi lain, misalnya panas. Untuk sistem tertutup, energi dapat berubah hanya jika energi masuk atau keluar, dan sistem dalam bentuk panas, kerja atau perubahan energi kinetik atau potensial sistem. Perubahan energi, ya, dapat ditentukan dalam keseimbangan energi sistem, ya. Terjadi keseimbangan energi sistem, ya. Hubungan antara energi yang ada di dalam, kecepatan, gravitasi, massa, dan ketinggian, ya, disebut dengan hukum keseimbangan energi. Kita bisa lihat hukum pertama termodinamika ini, ya, ada dalam video berikut, ya.
First law of thermodynamics. At the end of this lesson, you will be able to state the first law of thermodynamics, illustrate the first law of thermodynamics, explain internal energy and enthalpy. Law of conservation of energy. The energy can be neither created nor destroyed. It can only be transferred from one form to another form.
Blabbermouths! Energy cannot be destroyed, only can be converted. I'm going to break this universal energy law. Let us see how the spring converts my energy. I proved it. My energy is not converted.
Energy cannot be destroyed. It can only be converted. When compressed, the spring stored elastic potential energy and released it. The energy can be of different forms. Heat energy, a form of energy which transfers among particles in a substance by means of kinetic energy of those particles. Electrical energy is the energy due to electron flow. Mechanical energy is the energy stored by a machine that induces motion. Chemical energy is the energy that bonds atoms in a molecule. From the conservation law, these energies can be converted from one form to another. Let us discuss these changes. The heat energy from the sun is absorbed by plants and is converted into chemical energy through photosynthesis. It is a natural process. And let us see few examples for artificial energy conversion processes. The conversion of electrical energy to mechanical energy in case of fan. Conversion of electrical energy into mechanical energy in home appliances like mixer, grinder, etc. The water heater is the good example for conversion of electrical energy into heat energy. In IC engine, there is a conversion of heat energy into mechanical energy. Conversion of chemical energy into heat and sound energy in crackers, and conversion of chemical energy to electrical energy in the battery. Moving further, another important classification of energies is potential and kinetic energy. Say a rock at some elevation possesses some potential energy. A part of this potential energy is converted into kinetic energy when it falls down. This energy conversion is called as first law of thermodynamics. One best example for chemical, heat, and mechanical energy conversion can be found in the working principle of steam locomotive engine. Let us have a close look into the conversion of these energies. Here, the chemical energy of the fuel is converted into heat energy when they burn. Let us denote the heat energy supplied by burning of this fuel as Q. Generally, the unit for heat is joule. And this heat energy is used to boil the water. Let us consider the initial temperature of water as T1. If we see at microscopic level, the water molecules will have rotational, vibrational, and translational movements all together, called as kinetic energy. And these atoms, when bound together, the binding energy of the atoms is the potential energy of these water molecules. This potential and kinetic energy combined together is known as the internal energy of the water molecule. Thus, internal energy can be defined as the sum of all microscopic forms of energy of a system, and the internal energy can be denoted as U. At initial level, let us denote it as U1. When the water is heated, the water is converted into steam, and these bonds are broken, and the water molecules start moving vigorously. This leads to increase in the internal energy. At this stage, the internal energy can be denoted as U2. During this process, the temperature has increased from T1 to T2. Let us denote the change in temperature from T1 to T2 as delta T, and the change in the internal energy from U1 to U2 is denoted as delta U. This change in the internal energy delta U depends upon the quantity of water and its specific heat capacity, that is, the heat required to increase the temperature of water by 1 degree Celsius, and also changes in temperature delta T. Thus, the change in the internal energy delta U is the product of mass of water and specific heat capacity and change in temperature. Now, the supplied additional heat is used to expand steam to push the piston in the steam engine. And thus, the total heat supplied is used to increase the internal energy and also to do work, that is W. Now, the total heat supplied Q is equal to delta U plus W. Work can be defined as the quantity of energy transferred from one system to another, and the work is measured in joules. Let us see the total heat content of this system, which is the sum of total internal energy U and work done W. As the internal energy and work are two different properties that occur frequently together, it has been added to give a combined property known as enthalpy or total heat content. This total heat content of the system is denoted as H. Work done can be given as the product of pressure and volume. From the first law of thermodynamics, that is, energy can only be transferred. The chemical energy of a fuel is converted into heat energy, which is then converted into mechanical energy that helps the locomotive steam engine to move. Summary.
Everyone must be knowing the first law of thermodynamics. But I know it better, so I will take the responsibility to summarize it. First law states that the energy can neither be created nor destroyed and can be converted from one form to another. Internal energy is the microscopic level energy, which is the sum of all kinetic and potential energies, and it is denoted as delta U. Enthalpy is the total heat content of a system, that is, the total internal energy and work done. It can be denoted as H, where product B and V indicates the work done by the system.
Topik kedua setelah thermal design adalah mesin desain. Ya. Topik kedua dari teknik mesin mechanical engineering, topik pertama adalah thermal design, topik kedua adalah mesin desain. Mesin desain atau perancangan mesin. Segala bentuk desain pada dasarnya adalah proses pengambilan keputusan. Proses desain melibatkan pengembangan rencana untuk memenuhi kebutuhan atau memecahkan masalah. Desain mesin adalah studi tentang perilaku mekanik, elemen mesin, dan proses manufaktur. Nah, video berikut menggambarkan bagaimana perancangan mesin dalam industri yang terkait dengan perilaku mesin. perilaku mekanik. Seorang insinyur di desain harus mampu menentukan kebutuhan material. Seorang insinyur desain harus mampu memahami kelas material seperti logam dan polimer. Seorang insinyur desain harus mampu memahami struktur mikro internal bahan yang dapat berupa kristal dan atau amor. Seorang insinyur desain harus mampu menggunakan diagram tegangan, regangan untuk menyatakan sifat material dalam 5 variabel teknik. Tegangan, regangan, batas elastis, kekuatan luluh, dan ketangguhan. Seorang insinyur desain harus mampu menggunakan hasil yang ditentukan untuk variabel tersebut untuk melakukan pemilihan bahan. Ya, itulah perilaku mekanik yang harus disepahami seorang mechanical engineering. Dia harus punya kemampuan ability. Bagian kedua dari mesin desain, ya, itu adalah elemen mesin. Elemen mesin terkait dengan komponen mekanis dasar yang digunakan sebagai bahan dasar sebagian besar mesin. Itu termasuk poros, roda gigi, bantalan, pengencang, pegas, segel, kopling, dan sebagainya. Proses manufaktur. Proses manufaktur ya proses fabrikasi, proses menghasilkan, ya, menghasilkan suatu produk. Mulai dari kita memilih material bakunya, ya, raw materialnya, memilih bahannya. Makanya tadi ada kemampuan harus mampu memilih, mengekstrak, ya. Kemudian kita mendesain dan memproduksi hasil desain, kemudian diproduksi, kemudian di packaging, ya, kemudian didistribusikan, digunakan. Setelah itu digunakan, kemudian dilakukanlah maintenance, ya, dan akhirnya recycle, ya, digunakan kembali, yang berguna, material yang berguna bisa disikluskan menjadi bahan baku ulang, ya, di recycle. Yang tidak berguna ya dibuang. Itulah proses manufaktur, bagaimana material dipilih, material dipisahkan, sampai akhirnya dia dirancang, dibangun, diproduksi, di packaging, didistribusi, digunakan di maintenance, kemudian dievaluasi, di-reuse, bisa di-reuse-kan atau di-recycle, ya. Kalau tidak ya dibuang. Kira-kira proses itu adalah proses siklis. Video berikut menggambarkan bagaimana proses dan klasifikasi dari proses manufacturing. Ya, kita bisa dilihat ada 4, ya, pokok utama yang ada dalam video ini. Bagaimana proses castingnya, bagaimana formingnya, proses formingnya, bagaimana weldingnya, dan material removal prosesnya.
What is manufacturing process? Give its classification. In our daily life, we come across goods produced in bulk from the raw materials with the help of machines. The process of producing such goods is termed as manufacturing process, and the goods produced are termed as manufactured goods. Thus, we can say that manufacturing process refers to the production of goods in large quantities using machines. It is basically classified as casting process, forming process, welding process, and material removal process. Let's first discuss about the casting process. Casting process is one of the oldest methods of manufacturing. Sand casting is one of the most common examples of casting, where the molten metal is poured into the mold cavity, and then it is allowed to solidify to produce the casting product. Some other examples of casting are investment casting, permanent mold casting, die casting, and centrifugal casting. Let's now discuss about the forming process. Forming process refers to the process of changing the shape of a preheated metal. Drop forging is one of the most common examples of forming, where the heated metal billet is placed in the die, and a hammer is allowed to fall freely on it. Due to the force applied by the hammer, the heated billet takes the shape of the die. Some other examples of forging are press forging, upset forging, wire drawing, and rolling. Let's now discuss about the welding process. Welding process refers to the process of joining two metallic workpieces by applying heat and pressure if required. Gas welding is one of the most common examples of welding, where the two metal plates are joined together either permanently or temporarily by applying heat and sometimes pressure if required. The heat which melts the metal plates is supplied by the combination of two gases, in which one gas is inflammable in nature. Some other examples of welding are electric arc welding, resistance welding, soldering, and brazing. And now let's discuss about material removal process. Material removal process refers to the process of removing any unwanted material from the work pieces. Drilling is one of the most common examples of welding, where the unwanted material is removed from the work piece by creating a hole in it. Some other examples of material removal process are milling, grinding, broaching, and turning. The related terms are
Demikian materi kita hari ini.
Wes angel iki angel.
Ada pertanyaan?